Swayam Prabha. Digital India. Educated India.
Hello and welcome to this Manufacturing Process Technology Part 1 Module 34. We were talking about the different peeling processes associated with the processes turning, shaping, planing and milling. We also wanted to see about the different kind of milling operations which are there, and in that context we had done earlier, we had seen the various orientations of the tool with respect to the workpiece in case of slab milling, slot milling, form milling, face milling, end milling, so on and so forth. So, typically you can classify also the milling processes into up milling and down milling. These are different illustrations of what happens. So, when the cutting and the feed motion are in the same direction, the operation is known as down milling. You can see the down milling happening here, that the workpiece is being fed in the same direction as the cutting motion or cutting action. The peeling process starts with the engagement of the cutter, which is rotating here in the clockwise direction from this top surface to the bottom surface. So, the peeling process is in the same direction as the direction of motion of the workpiece, and simultaneously when the cutting and the feed direction are in opposite directions to each other. In this particular case, for example, the cutter is coming down in this manner and it's engaging here to peel off, and the feed of the workpiece is happening exactly in the other direction of the direction of cut. So, this is called the up milling operation. So, there are various issues associated with up and down milling, and you can define them as in conventional milling, which is typically an up milling process. The feed movement is opposite to tool rotation with the different main highlights here, where the width of chip starts from 0 and increases. You can see here in the up milling process that the width when you start with the first engagement is smaller, and the width keeps on increasing with the chipping action happening. The tooth meets the workpiece at the bottom of the cut. Upward force tends to lift the workpiece, so there is a tendency of the workpiece to go up because of the engagement, and therefore more power is required, and rubbing is provoked by the chip beginning at minimum width, and the surface finish is marred or spoiled due to the chips being carried upward by the tooth, and chips fall in the front of the cutter. That is another problem in this particular case, which makes the chip disposal become little difficult, because the chip which is generated here would try to by gravity actually come down on the finished area of the workpiece, and so therefore there is a general faster wear on the tool than the other case, which is the climb milling or the down milling. So, this is known as the climb milling or the down milling, where the feed movement and the tool rotations are in the same directions. Here obviously the width of the chip starts at a maximum and then decreases. As you can see here, the maximum engagement is added towards the beginning, and then as it goes off, the chip peels off, it is going to become a thin section as the peeling happens, and the section is finally going to be as thin as possible at the point of peel, okay, of the chip from the surface. So, the tooth meets the workpiece at the top of the cut. Easier chip disposal, chips are removed behind the cutter. So, basically you can say that at least the finished part or the finished surface is not affected by the chip, because the chip whatever would go will go down in the area which is again to be cut, okay. So, you have less wear and increases tool life up to about 50%. It results in improved surface finish, of course. The chips less likely to be carried by the tooth into the finished zone, and so less power is required. Cutter with higher rake angles can be used, and climb milling exerts a downward force on the workpiece, which is again easy for a machining situation involving a lot of fixture design, etc. So, in this case the fixture design cost is not very significant, because already there is a downdraft on the or the downward pressure on the workpiece because of the relative orientation of the tool with respect to the workpiece. So, having said that, let us now actually start looking into the mechanistic aspects of drilling, In this particular case as well, you can see that there is a peeling motion which is happening here by the two edges, at the end of the drilling cutter, and there is a peeling action happening, as you can see right about here in this region, which is similar to what is happening in all the other different processes like milling or lathe or shaping, planing, etc. So, the same peeling action. So, let us now finally get into studying of this peeling action little better. This is a peeling action which is going on here, right about expressed in this particular figure. So, this is the uncut surface, and you have a tool point or a tool tip, which is actually a single point tip though, but then there is a cutting edge which is associated with this, and it moves with respect to the workpiece in a direction which is parallel to the direction of movement of the workpiece. So, the tool is in the same in the direction parallel to that of the workpiece. This in fact is the tool edge which is performing the cutting action, okay, and this is a part of the tool here again, and you have a motion or a velocity of the tool v due to which the chipping action is going to happen. This is of course the chip which is being formulated. So, the upper surface of the chip is always a rough surface, because of you can think of it that the tool actually tries to remove the metal as a pack of cards, and it tries to create different sections where there are some kind of interlayer stresses which are generated, because of which there is a jaggedness on the top of this chip which is being created here, as you can see, and the bottom surface remains planar because it goes more so with respect to the face of the tool, and so it leaves a shiny surface on the surface of the chip. So, the angle at which this chip comes off the surface is known as the rake angle, and simultaneously the face of the tool which faces the chip is known as the rake face, and you have the other side of the tool which is also sort of overriding the finished surface, which you can see right here. This is the finished machined or finished surface of the particular tooling operation or machining operation. So, here you can see that there is an angle which is formulated between the face here and the surface, and this is normally known as the relief or the clearance angle, because if this angle were 0, then the tool would rub on the surface of the finished material, and that would spoil the quality of surface finish related to the machining. You have also a shear angle which basically is made by this shear plane at a certain instance of time where the shearing action is happening, and as if the push of the tool is trying to remove this out in this particular direction, because the tool is now moving in certain relative motion with respect to the workpiece. Okay. So, there is going to be always a angle formulated here at certain angle, which is again as I will probably later on illustrate, is going to be the angle corresponding to the minimum power consumption for the tool, and that would lead to formulation of this shear angle. So, you have a uncut chip thickness which is actually the area which is being grazed away or grazed off as a chip, and then there is a cut chip thickness which is this TC value here, which is actually the final thickness after deformation etc. of the chip that takes place on it. So, having said that and having clearly illustrated all these different parameters, let us now play around a little bit with the different angles and geometries and forces that are associated with respect to this machining process. But before doing so, I would just like to again sort of categorize this process as a orthogonal and oblique cutting process. So, in the orthogonal process, typically the cutting edge is perpendicular to the direction of velocity of the tool. You can see here the cutting edge is exactly perpendicular to the direction of the tool motion, okay, which is actually in this case it is being shown as the direction of the workpiece motion though, but the tool motion can be thought of as relatively moving against the direction in which the workpiece is moving. So, it is in this particular direction, and this edge here of the tool is exactly perpendicular, but in cases where it is not perpendicular, as you can see here, for example, the tool is moving in an oblique manner, or with respect to the workpiece. The workpiece is moving in a straight direction here, but the tool is moving in a certain angle. So, these are known as oblique cutting. So, when the cutting edge is at an angle not equal to 90 degrees to the direction of velocity of the tool, the cutting is oblique cutting. So, these two theorizations are completely different. We are going to now consider the orthogonal cutting action, and if time permits, maybe do some oblique cutting, but by and large we will focus on to this orthogonal cutting operations related to mostly used form of cutting within the industry. So, let us now look at the geometry aspects of how the chip gets formulated. So, you have a workpiece here, right about here, and you have a chipping process which happens in this particular zone right about here, okay, due to which there is a formulation of a finished surface which comes up, and let us say there is a tool that I have introduced here as shown by the shaded region, and obviously this tool is at an angle with respect to the perpendicular drawn at this particular chip workpiece tool interface. So, this angle is really the angle that the tool's rake face makes with respect to the perpendicular, and I call this angle alpha. I think I had just illustrated earlier in the earlier diagram how this rake angle or rake face can be defined, and obviously you have a certain direction of the chip velocity, which is actually chip is moving in this direction. So, I would say that the chip velocity is also in the direction of movement of the chip, okay. And if I really take the thickness of the cut and the uncut surfaces here, I would extend this particular plane all the way backwards to find out what is this thickness. Let us call it T1, which is actually in this case the uncut chip thickness, and I would now utilize this particular thickness right about here, which I call the cut chip thickness T2. Okay. So, this is the cut chip thickness. So, having said that, now you have various parameters like the uncut chip thickness, the cut chip thickness, the rake angle, the chip velocity, the tool, so on and so forth. And obviously, there is this plane formulated here, which is also known as the shear plane, okay. And the angle that is there in turn is basically the shear angle. So, this is the shear angle, and I would just draw a small perpendicular from this particular point here, which I call S, okay, which is the end of the zone where the chip formulation is taking place. Let us call this point O, and let us call this point M, and then if I just move the perpendicular from the point S to the tool surface, I call there are 2 points which I will hit. One is on the chip itself, which I call the point Q. The other one is on the tool surface, which I call the point P. Okay. So, we also drop another perpendicular to this tool surface right about here in this particular case, you know. So, we have one perpendicular on the axis, one perpendicular here starting from the zone where the chip formulation ends on the workpiece surface all the way to the tool surface, and then there is another perpendicular we want to just make on the top of this tool surface right about here from S, and we call this point of intersection N, okay, on the tool surface. So, this point right here is called N. So, we have a perpendicular here on this particular tool surface. So, having said that, now if I look at the triangle O S n. Yeah. So, in this just I have just relayed the figure a little bit just for the sake of understanding. So, you see then again the same points S, O, N, P, and this Q is now this point here, right about here, where it is the vertical intersecting with the perpendicular projection of the point S onto the tool surface, okay. And the shear angle here is phi, for example. This is N point where the perpendicular from S to the tool surface happens, and that is how the geometry is, okay. So, if we do again the various geometrical considerations here, the angle PSN, which is actually this angle right about here, should be equal to the angle POQ, which is actually this angle right here, and that is alpha. The reason being that if I were to look at angle OPQ, the angle OPQ in triangle again OPQ with angle POQ being equal to alpha should be equal to 90 minus alpha, and with the same angle 90 minus alpha, if I look into triangle PSN, which is also a right triangle, the angle PSN should be equal to again 90 or 180 degrees minus 90 plus alpha. So, angle PSN should be equal to 180 minus 90 minus alpha, which should be actually equal to alpha, okay. So, we have this angle PSN and angle POQ being equal to alpha, or angle NSO, which is actually equal to the angle here right about here, should be equal to the angle PSO minus the angle PSN, and angle PSO is nothing but phi, because these are alternate angles and they are equal to each other. So, phi minus angle PSN, which is actually equal to alpha in this particular case, is the angle NSO. So, having said that, now I have two formulations here, one talks about angle PSN, angle POQ, and another talks about angle NSO. Now, if I were to see the length OS divided by the length SN, it should be equal to the secant of phi minus alpha. Or in other words, the value Sn here, which is actually represented by this particular length here, should be equal to OS cos of phi minus alpha. So, the value Sn is actually equal to T2. If I may just recall, this T2 and this Sn are parallel to each other, and therefore, I can say that OS becomes equal to T2 by cos of phi minus alpha. Further, the triangle SMO includes the side OS as one of its sides, is the hypotenuse, and I can represent OS here from this triangle to be equal to Sm by sine of phi. So, therefore, this Sm by sine of phi further would mean T1 by sine phi. Thus, we have an expression T1 by sin phi equal to T2 by cos of phi minus alpha. In other words, T1 by T2, which is actually a very important component. So, which is a very important component also known as the chip thickness ratio, is defined now as sin phi by cos of phi minus alpha. So, we are going to do this, take up this up further, but in the interest of time we will like to close this particular module. In the next module, we will try to actually go ahead and see how this chip thickness ratio would be able to influence the different shear stresses and strains which are needed to make this chipping process happen. Thank you so much.